students. We are back with another lesson. In this lesson, we'll derive the expression for path difference, position of secondary maxima, and secondary minima. So let's start with the expression for your path difference. So in our previous class, we have discussed diffraction. So in diffraction, you had a source of light. This source of light was producing wavefront in all directions. Now, the light produced or the light waves produced by the source of waves is focused into the slit of size d, slit with small d, using your lens L1. Fine. Now, when the lens passes through the slit, this slit will act as the source of your secondary wavefronts according to your Huygens principle. Now, the wavefronts produced by the slit AB is being focused on the point O using your lens L2. Now, if all of the lens which was focused on this point O do not have a path difference, or I'll say if the light waves coming from here and here, if they don't have any phase difference, then at this point O, you had a central maximum. Now, let us consider the another rays. These rays are diffracted at an angle theta. Can you see they are moving at an angle theta? Now, because these rays are diffracted at different angle, in such case, what happens? If you focus this light, let us say on the point P, there is a path difference coming into the picture. If you consider the light which moves from this point A and the path followed by the light which starts from point B, they do not cover the same path. Therefore, a path difference comes into this picture. The extra path which your light has to travel if it is traveling in this direction. So because of this path difference, at this point on the screen, we will get a secondary maxima or your secondary minima depending on the path difference. Fine. So first, let's derive the expression for this path difference. So if let us suppose the angle by which the rays are diffracted. Let this angle be theta, okay, and these rays are focused at the point P on the screen. So in this case, let us consider the light, okay. Suppose the light starts to move from this point A and it is being focused at this point P using your lens L2. Similarly, consider your another light which starts from this point B, which is being focused on this point P using your lens L2. Fine. Now, in this two case, okay, the light which starts from the point A and the light which starts from the point B, they do not travel the equal path, okay. This path is not equal to this path. The light which starts from this point B has to travel a extra path, and this path is given by this Bn. Okay, the extra path travel is shown with Bn. Okay, I'll draw using a green pen. Fine. So in our case, the path difference, the extra path the light has to travel will be given as the path or the distance traveled by the light from this one B to P, BP, minus the path or the distance the light travel from the point A, which is your AP. So your path difference is BP minus AP. and the extra path is given as bn. Right now, let's focus on this triangle. Okay, let me just zoom in here. Okay, fine. Now, consider your triangle A, B, N. This yellow triangle. Fine. Consider this yellow triangle. Now, in this triangle, this angle is your theta. Fine. This distance, AB. AB is known as your slit width, which is given by small d. Fine. We need to find out this distance BN. To find out this BN, I can use the trigonometric ratio sine theta. So for this triangle, sine theta will be the ratio of the opposite side divided by your hypotenuse. Fine. Sine theta equals to Bn upon AB. And we know the slit width AB is given as small d. Fine. So instead of AB, I can substitute small d here. Now I can send this d to the other side. So I can write Bn equals to d sine theta. Fine. So the extra part traveled in terms of your slit width can be written as d sine theta. Fine. So your Bn equals to d sine theta, which I can substitute here. Therefore, your part difference expression can be written as P equals to d sine theta. Fine. So this is an important relation which we'll be using. Fine. So let me put this in a box. So the part difference expression equals to d sine theta. Fine. Fine. Next, we will derive the expression for the position of minima. Now, to obtain the position of the minima, the part difference should be the multiple of lambda. Fine. In my last class, I have showed you if what happens if the part difference is a multiple of lambda. In that case, what happens? You have to divide this slit into two halves, region 1 and region 2. The light which is produced by the waves which are coming from your region 1 is being cancelled by the region 2. Hence, at this point, you receive or no light. Okay, there will be a destructive interference and this point. And this point corresponds to your first secondary minima. Fine. So for your first secondary minima, the path difference is lambda. Fine. If you have any confusion how we got the your first secondary minima at this point, I will strongly recommend you to go back to my previous video. Fine. But if you still have confusion why we are getting a secondary minima, please don't hesitate to ask. I will re-explain it to you again. Okay. For now, you can consider when the path difference is lambda, you will get a first secondary minima at this point P. So let us consider, suppose your light, the light which is produced is diffracted at an angle theta 1. So when the light is diffracted at an angle theta 1, it produces a path difference of lambda. Fine. So when the path difference is lambda, okay. So at that point, what you will do, you divide the slits into two halves such that at this point, okay, at your sixth position, okay, what happens? The path difference will be how much? Lambda by 2. Fine. In such case, what happens to the light which is produced by the point 0 and the light which is produced by the point 6, the light which comes at this point P, and the light which comes from this point 6, they have a path difference of lambda by 2. And if there is a path difference of lambda by 2, then there is a phase difference. The two waves coming from here and here will be out of phase with respect to each other, and at this point you will obtain a destructive interference. Fine. If the two waves interfere destructively, hence you won't receive any intensity at this point. So this point will represent your first secondary minima. Therefore, I can also say this one as your first dark fringe. Fine. So let's write the condition for the first dark fringe. So the condition for the first dark fringe is when the path difference, we have derived the expression for the path difference equals to d sine theta. Fine. But in this case, we are considering for the angle theta 1. Okay, this angle theta 1 represents the angle for which you will get the dark fringes. We are considering for first dark fringe. So I can write d sine theta 1. So when the angle at which the light is diffracted is theta 1, in that case the path difference is lambda. So I can write d sine theta 1 equals to lambda. So this is the condition for your first dark fringe. Fine. Fine. This one was your first dark fringe. Now let us derive the condition for your second dark fringe. For second dark fringe, consider another point P. Fine. Consider one more point P such that this time the rays are being diffracted at an angle theta 2. Fine. Earlier it was theta 1. Now you consider the rays are being diffracted at an angle theta 2. Now consider the light which is produced by all this point on the slit width are being focused at this point P at an angle theta 1. Fine. So all of the lights are produced at this point P. Now note, when your the diffraction angle is how much? Theta 2. In such case, if you draw a perpendicular distance, remember you always draw a perpendicular distance. Okay, so why we need to draw this perpendicular distance? Because if you consider this path and if you consider this path, they are equal. Fine. All the distances which are behind this perpendicular distance, behind this green path, okay, this is the extra path which your light has to travel. Fine. Now let us draw a perpendicular distance AN. Now in this case, when the light is diffracted at an angle theta 2, fine, this angle will represent how much? Theta 2. Fine. In such case, the extra path traveled, this distance, the extra path traveled will be how much? It will be twice of lambda. Fine. This is two wavelength. Okay, let me just write down in notations. Fine. So you have to remember when the light is diffracted and at an angle theta 2, the path difference is 2 lambda 2. Okay, twice of lambda. Now in this case, what you do? Again, divide your slit width. Okay, but this time instead of dividing into two halves, we will divide into four halves. Okay, we'll see why. Okay, look here. Now, if this path difference is 2 lambda, so up till this distance, okay, can you see this distance? This distance will be half of this distance. If this is 2 lambda, then this distance will be lambda. Fine. If this distance is lambda, okay, then if can you see this distance? This distance will be half of this distance. Fine. So if this distance, the light coming from this 6 is how much? Lambda, then this one will be lambda by 2. Fine. So, did you get the idea how I've divided the various part difference in various lambda terms? Okay. So why we are doing this rigorous mathematics here? This is just to show that consider the light which is coming from this point 0. Consider this distance and consider the light which is being produced by this point 3. Obviously, the light has to travel the extra path difference, but in this case, how much is the extra path difference? Lambda by 2. And if the path difference is lambda by 2, what happens? The two waves produced from here and here will be out of phase. Okay, if you forgot what happens if there is a out of phase, okay, you can consider like this. Do you remember this relation? Your phase difference phi equals to twice pi lambda p. Fine. Now consider in this case, what is the path difference? Lambda by 2. Substitute this value here. So this becomes lambda by 2. Fine. If this becomes lambda by 2, you can cancel this lambda and you can cancel this 2. So in this case, what happens? The phase difference is how much? Phi. What does this phase difference means? The light which travels from this point. Okay. There is no phase difference for the light which starts from this point A. But since there is a path difference of lambda by 2, for path difference of lambda by 2, the phase difference corresponds to pi. That means the light which starts from this point will have a phase difference of pi. Okay. So, so for this, you can consider this one. This is the light wave coming from this point A. Fine. From this point A. So there is no phase difference in this case, but the light which is coming from this point 3, it has a path difference lambda by 2 which corresponds to a phase difference of pi. That means the light is traveling a extra phase of how much? Pi. So what happens if I introduce a phase difference pi? Can you see? In this case, the red wave crest and the blue wave trough, they will interfere with each other and you will get a resultant wave will be 0. Fine, the two waves will cancel each other. This is your destructive interference. Okay. So in this case, if there is a phase difference of pi, what happens? The two waves cancel each other. Fine. So you can assume the waves produced by the first part is being cancelled by the second part. Similarly, the waves produced by the third part is being cancelled by the waves produced by the fourth part. So therefore, at this point, you will get no interference. Okay, at this point, you will get only destructive interference. That means no waves here. Therefore, you will get another dark fringe at this point. And this dark fringe will be your second dark fringe. Fine. Or for simplicity, you can simply assume when your angle theta equals to theta 2, in that case the path difference will be how much? 2 lambda. And at this 2 lambda, what happens? You will get another dark fringe. This dark fringe is known as your second dark fringe. So the condition for your second dark fringe will be the path difference d sine theta 2 equals to 2 lambda. Fine. Fine. So similarly, you can assume for the another angle, that is for theta 3, the path difference will be how much? 3 lambda. For theta 4, what will be the path difference? 4 lambda. Theta 5, path difference 5 lambda, and so on. Fine. So we can write a general expression after observing these two conditions. Hence, the condition for the nth dark fringe can be written as d sine theta n equals to n lambda, where this n can take the values from 1, 2, 3, and so on. Fine. Fine. So this is the condition for the nth dark fringe. Fine. Now, now if you consider this angles, okay, these angles are very small. If these angles are very small, then I can write sine theta as theta n. Okay, I can simply write sine theta as theta n. So if sine theta is theta n, then I can write d sine theta n as d of theta n. Fine. So using this expression, I can write d theta n equals to n times of lambda. Fine, I can write this condition here. I can send this theta to the other side. Sorry, I can send this d here in the denominator. Fine. So this represents the angles. At what angles I will get the dark fringes. For the first order dark fringe, substitute n equals to 1. That means at an angle of lambda by d, I will get my first dark fringe. For your second dark fringe, substitute n equals to 2. That means this will become 2 lambda by d. So when this angle is how much? 2 lambda d. In that case, at that point, you will get a second dark fringe. Similarly, you can do for second dark fringe, third dark fringe, fourth dark fringe, and so on. Fine. So this angle, okay, the expression of this angle represents the position position of your minima. At what positions you will get your minima will depend upon this angle. Fine. So this expression is the position of the minima. Fine. So for this expression, the position of the secondary maxima. Okay, we'll do it in our next class. Fine. So up till the expression of the path difference and the position of minima. If you have any confusion, please don't hesitate to ask. I will re-explain it to you again. Okay, and in our next class, we will derive the expression for the secondary maxima and then we will derive your angular width. Fine. So from your board's perspective, okay, from the board's perspective, only the expression is important, okay, not this derivation part. You can remember only the expression. What is the expression of the path difference? What is the position? At what angle you will get your minima? You can only remember this angles. No need to remember this whole derivation, okay? They don't ask the derivations. They will just give multiple choice questions where they will ask this expression. Fine. Okay. So again, thank you.